Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College in the midst of Silicon Valley, and I'm delighted to welcome everyone here in the Smithwick Theater and everyone watching us or listening to us on the web to this talk in the 14th annual Silicon Valley Astronomy Lectures at Foothill College. We have 6 times a year exciting talks by noted astronomers on new developments in our understanding of the universe. And tonight is an especially interesting talk in our series. The talks in general are jointly sponsored by the Foothill College Astronomy Program, by NASA's Ames Research Center, by the Astronomical Society of the Pacific, and the SETI, or Search for Extraterrestrial Intelligence Institute, and we're very grateful for their help. Our speaker tonight is Dr. Michael Bicay, who's the Director of Science at NASA's Ames Research Center, leading more than 400 scientists and technical staff who conduct research in space, Earth, and biological science. Dr. Bicay's PhD is in applied physics from Stanford, and his research interests include many different parts of the universe. He's interested in the properties and contents of galaxies and galaxy clusters. He's been interested in the infrared astronomy, which will form the main part of his talk, and in the large-scale structure of the universe itself. Before he came to Ames, Dr. Bicay was on the scientific staff at the California Institute of Technology Infrared Processing and Analysis Center, or IPAC, and he was the program scientist at NASA headquarters for a number of years. He also served as an astrophysics consultant while he was in Washington to the National Air and Space Museum. After returning to Pasadena, Dr. Bicay was a scientist and the scientific community liaison for the Spitzer Space Telescope, which is going to be the topic of his talk. As many of you who enjoy astronomy know, in astronomy we don't limit ourselves to what our eyes can see. There are whole branches of astronomy that are invisible to the eye, but accessible to our telescopes. So here to tell you more about lifting the cosmic veil, a decade of highlights from the Spitzer Space Telescope, it's my honor to present Dr. Michael Bicay.
Thank you, Andy, and thanks for coming out on such a glorious evening tonight. I can tell you a little bit more about tomorrow's press conference. It is at 11 a.m. Pacific time. It's a major announcement from the Kepler project at Ames, and it's guaranteed to be front page news in the Friday newspapers. So you can log on to nasa.gov and watch it on NASA TV tomorrow at 11 a.m. So I wanted to talk to you about a project that's not based at Ames. It was at one point, and I wanted to talk about the Spitzer Space Telescope. And the reason I'm talking about it is because I spent 14 years of my life working on Spitzer, 8 years directly on the project at Caltech, and 6 years indirectly while I was a program scientist at NASA headquarters in the 1990s. And so it's been a long road to get to where we are, and when Andy asked me to give this talk on infrared astronomy, I did not have a canned presentation, so I actually had to work and put something together. But it was a labor of love because Spitzer has been operating now for about 10.5 years. And if you go to the website, which is spitzer.caltech.edu, you will find roughly 400 image releases and press releases that have come out over the last decade. And it was hard for me just to narrow it down to a manageable plateful tonight, but it was a lot of fun, and it brought back a lot of fond memories. So tonight my intention is to tell you a little bit about how we got the program approved, and then to feature some of the highlights from the Spitzer Space Telescope. So let me start the story more than 200 years ago. In fact, it was in 1800, and you probably know the name William Herschel. You probably know him as an astronomer who built telescopes, but he did a lot more, as did many of the Renaissance men back in the 17th and 18th centuries, and 19th century for that matter. So he was a musician. He compiled astronomical catalogs of stars, double stars in particular, and nebulae. And of course, we all know he discovered Uranus, the first new planet since antiquity. But in the year 1800, and this is a reprint from an article he published back then, he did something interesting. He was wondering about whether the colors of the rainbow actually translated into different thermal temperatures. And so he set up an experiment, and you see a reproduction of it here on the right, where he took thermometer bulbs and blackened them and put them in the different colors of the rainbow after he had separated the light from the sun via a prism. And he found different temperatures in different colors of the rainbow. And so naturally, being a scientist, he said, well, what's beyond what I can see? And so he put a thermometer bulb longward of the red end of the spectrum and found out it was a different temperature than anything he saw in the visible light. So he called these things calorific rays, which is a derivative of the Latin word for heat, and found that these rays, even though they were invisible to our eyes, were reflected, refracted, absorbed, and transmitted just like the visible light. So this really was the dawn of the non-visible light era in physics, and it's led to a revolution in our understanding of the universe. And so why do we look in the infrared? Well, here's a couple of quick pictures that demonstrate why we do that. Things look different. And this reminds me, acoustic waves, sound waves, are not the same as visible light waves. But I did a little experiment when I was down at Caltech, and I was doing an education project down there. And what I did is I took Beethoven's Ninth Symphony and recorded it. And then I filtered out everything except for a narrow band that corresponded to visible light. And you couldn't even recognize the music. It was completely unrecognizable. And the point was to fully understand and appreciate the beauty of Beethoven's Ninth Symphony, the last movement. You need to hear all of the instruments. And so the analog, I would say, is to appreciate the beauty and complexity and the physics of the universe. You need to understand, you need to view at a wide variety of wavelengths. And we've done that now, and that wasn't the case 20 or 30 years ago. And I'm going to tell you a bit of a story about how we got here tonight. So astronomically, this picture, unfortunately, the color rendition is not the best here, but this dramatically illustrates how different the universe looks. On the left, of course, is the familiar constellation of Orion. On the right is what it looks like in the far infrared. And it's a dramatically different view. And so as we go forward, I'd like you to understand that I'm going to be talking about the contents of a spiral galaxy, much like our Milky Way. And so when you look up on the left, you see all these points of light and stars. And if you add up all of the masses of those stars in a galaxy like the Milky Way, you come up with a number like 10 to the 11th. So that's one with 11 zeros after it, solar masses. And then about, roughly 10% of that is another part of the galaxy we do not see with our eyes. It's gas, both neutral and atomic gas. And then another factor of 200 down from that is dust. And so if you really want to conduct a census of any spiral galaxy, it's inadequate just to look at the stars. You need to count the gas and the dust, which we collectively refer to as the interstellar medium, or the ISM. And that ISM is primarily, at the 98% level, is primarily hydrogen and helium, and the remaining couple of percent are the heavy elements, anything with an atomic number beyond 2. So I'm going to be showing lots of pictures tonight of dust. And you might think, well, what's the big deal with dust? Well, dust is the material from which future stars form. Think of it as a reservoir for future star formation, and you'll see plenty of that tonight. And these dust grains are on the order of 1/10 of a micron, where a micron is 1/1,000,000th of a meter in diameter. And the dust are composed of, in many cases, a material that you're familiar with here on Earth, silicates and amorphous or non-crystallized carbon. And so before we go further, I wanted to show you this series of portraits of the center of the Milky Way galaxy. I'm not going to step through all of these, but the point is, if you look at the third from the bottom, that's what the Milky Way looks like at optical wavelengths. A lot of dust is obscuring our view of the inner bulge of the Milky Way galaxy, but if you go into the near infrared, you poke right through that and you see the stellar bulge. And then as you go to longer wavelengths, you actually see more of the dust. And so yet another indication of why we want to observe our own galaxy and the universe at a wide variety of wavelengths. Now, I was asked to put together a non-technical talk tonight, and I think I only have a few graphs in here. But I wanted to talk about nomenclature just for a minute here. So, we're going to be focusing on the infrared part of the electromagnetic spectrum. So, the long word of the red that you would see in a rainbow. And I've blown up on the bottom here, visible on the left and submillimeter on the right, and in between are various infrareds. And these are not clear delineations. They're somewhat arbitrary, but if we observe from 1 to 5 microns, which is roughly 10 times the wavelength you can see with your eye, we refer to that often as the near infrared, and you can actually do some of that from the ground. Once you get into the mid-infrared and the far infrared, which are more, it's thermal radiation, then you really do, for the most part, need to get above the obscuring water vapor in the atmosphere. So I'm going to be referring to a micron, which I said is a millionth of a meter, but for practical purposes, it's important just to remember that the diameter of a human hair is on the order of 50 to 80 microns. So the wavelength is thinner than the diameter of a human hair. I'm also going to be talking about temperatures, and I think most of you are familiar with Fahrenheit and Celsius. You may be less familiar with Kelvin, which is the scale that physicists and astronomers use. Kelvin is basically the same scale as Celsius or centigrade. It just has a different 0 point here. So what we refer to as absolute zero, which is the coldest possible temperature of about minus 460 degrees Fahrenheit, is defined to be 0 here. And so I'm going to be referring to temperatures of tens of K, or Kelvin, and hundreds of K. And it may sound warm to you. It's not warm. It's hundreds of degrees below 0 Celsius. So as I alluded to, we live in a rather dusty universe. And so what happens is ultraviolet and visible light from the stars hit a dust grain. They warm up the dust grain, and we see re-radiation in the infrared. And so I'm going to be showing lots of photographs of this, and I'm going to be explaining why this is important that we study this phenomena. Now, the paradox of infrared light is shown by these two illustrations here. At short wavelengths, we poke through the dust. So here's an image of the Galactic Center, visible light, near infrared light. We poke through a lot of the obscuring dust, but not all of it. So at short wavelengths, we actually can see through the dust, hence lifting the cosmic veil. At longer wavelengths, we actually see the dust. And so there are two different physical phenomena here. So that's the beauty of infrared light. And Spitzer covers both types of these wavelengths. And so we can see through dust when we need to, and we can see the dust when we want to. Now here's the perspective of an infrared astronomer, a slightly different version of the electromagnetic scale. Now, Andy, I assume since this is being filmed, you can put in a laugh track afterwards. This constitutes humor if you're a physicist or astronomer, okay? Moving right along. Here I've reversed, this picture reverses the EM spectrum, so the long wavelengths are over here now on the left and short wavelengths on the right. And so this explains why we have to go to space, or at least to very high altitudes to do most of infrared astronomy. So atmospheric absorption, in these wavelengths, it's mostly water molecules in the atmosphere, and they absorb infrared light from the cosmos. So we can do a little bit, we can do visible light astronomy from the ground, obviously. We can do radio astronomy from the ground. We've been doing it since the 1930s. But for most of the other wavelength regimes, we do have to get into space. Now, what's the big deal with infrared astronomy? Well, these three pictures, I think, illustrate what the big deal is. So in the upper left-hand corner, these are what we call black body curves. And so these represent how objects like stars radiate when they're in thermal equilibrium. And the couple of points I wanted to make here is that cooler objects emit less radiation overall. And the peak of their emission moves from the visible part of the spectrum longwards to infrared wavelengths. And much of the universe is cool. Our sun has a surface temperature of about 5,600 Kelvin. And so it peaks here in the visible light. It's a yellow star, okay? As you move to longer wavelengths, we're starting to sample a different regime of the universe, the cool universe. Another reason I've already alluded to, you can poke through dust, at least at the near-infrared wavelengths. And the one that I think most of you are familiar with is we live in an expanding universe. And as the universe expands, there's a redshift effect here. It's stretching out the light. And so the visible light emission that may be emitted in the distant universe comes to us as infrared light. And so if you really want to understand the very earliest primeval era of the universe, you need to best study it in infrared light. So the way we called it at Caltech is we study the cold, the old, and the dirty universe. So the early days of infrared astronomy started probably in the arguably in the 1960s. I said you had to get above the atmosphere. Here are some of the things we discovered or studied with infrared light in the early days. So we used high-altitude balloons that could get up to 100 or 110,000 feet. We used sounding rockets, which were suborbital. We flew small telescopes in a port that looked out the side of a Learjet. And for more than 2 decades, we flew the Kuiper Airborne Observatory out of Moffett Field here and Ames Research Center. And they laid the foundation for everything that we've done in the last 20 years in infrared astronomy. So I'm not going to go into great details here other than to say it's interesting some of the things we now take for granted, such as thin, tenuous rings around Uranus and an atmosphere on Pluto, were actually discovered in the infrared regime. So astronomers have been doing something that no other science discipline does, and that is for 60 years now, we get together as a community every 10 years, and we look ahead and we prioritize what we would like to do in space-based astronomy and in ground-based astronomy. And it's called the National Research Council Decade Survey. And now other scientific disciplines, not only in space science, but even in non-space science disciplines, are starting to follow this motif. And the advantage of this is it marshals the community behind a prioritized list of objectives that you tick off as Congress allows you, as funding becomes available. And Congress now recognizes the importance of these decade surveys. And so the first one to mention an infrared telescope was back in the 1980s, the Field Committee report. And they envisioned something called the Shuttle Infrared Telescope Facility, which leads to a very clunky acronym called SIRTF. And they envisioned this as being something that would go up on the shuttle. You would observe the infrared universe, and then bring the telescope back down, and so on, and update it and put new instrumentation as necessary. Well, that was the original goal, and you can see the date on this report here is October of 1980. So this was the current, what we envisioned SIRTF to look like. It's a relatively modest-sized telescope, 1 meter in diameter or less, and it would routinely go up to the shuttle. And in fact, NASA issued a competitive solicitation in May of 1983, and I've underlined a few key statements here. They anticipated building a telescope that would go into the bay of the shuttle. It would fly many times, return to Earth for refurbishment. Now, keep in mind, this was in an era when we thought we would be flying the shuttle 50 times a year. That's 50. And of course, we never even flew it more than 9 times a year, and that was in the mid-1980s. And so, that led to some changes in thinking. But what really opened our eyes was this first all-sky infrared mission called IRAS, the Infrared Astronomical Observatory. It was an 11-month mission that flew in 1983. And when I was getting my PhD at Stanford, I was actually doing my work down in Puerto Rico at the Arecibo Observatory. And I wrote some proposals and ended up analyzing some data from IRAS, and that's how I more or less transitioned from a radio astronomer to an infrared astronomer. Now, IRAS was an Explorer-class mission, so it was a relatively inexpensive mission, and it flew a rather modest-sized 57-centimeter telescope that was cooled down to 4 degrees Kelvin, 4 degrees above absolute zero. So it was a very cold telescope, which you need to detect the infrared light, which is basically heat coming from the distant universe. And the thing I like to amuse people with is the fact that IRAS flew with 62 pixels, 62 detectors. And now we build these large CCDs that are 2,000 by 2,000 pixels. We had 62 pixels on IRAS, 4 of them which didn't even work. And we flew IRAS in a 900-kilometer orbit around the Earth. And you can see in the lower right-hand corner, that's where this image came from. We discovered that the galaxy was full of what we called infrared cirrus. We called it that because it looked like cirrus clouds in the Earth's atmosphere, but it's really just infrared light coming from dust. We also discovered that when we pointed IRAS, and it was an all-sky survey, but when we looked at some nearby stars, recall that the radiation, if it was just from the star, would fall off as you go to longer wavelengths. We saw some surprising results with IRAS. We saw some bumps on that radiation distribution. That suggested there was some kind of infrared excess around these stars, and we did not have the spatial acuity to see where that excess was coming from. But we inferred that these stars were surrounded by some planetary disks that could be the formation remnants of solar systems. And then IRAS also discovered something we call starburst galaxies, where so much star formation is taking place that they're 10 to 100, even 1,000 times brighter than the Milky Way galaxy. So also a few years later in the mid-1980s, this is before I went to headquarters, the astrophysics director at that time came up with a clever marketing ploy called the Great Observatories, which is a phrase I think you've heard of. And everybody, of course, has heard of the Hubble Space Telescope. That is one of the 4 components of the Great Observatory program. And he put together a cartoon book, and it really is a cartoon book. And this was one of the pages of it. And it showed NASA's plan to build 4 telescopes that would cover different regimes of the electromagnetic spectrum. And so they included, and some of the names have changed, but it had the Hubble Space Telescope, which would observe the universe at visible wavelengths, and has been doing so since 1990. It does a little bit of infrared, but it's mostly visible light. It had something called the Compton Gamma Ray Observatory, which was launched in 1991, observed the universe obviously at gamma rays, very high energy gamma rays, and it was deorbited. That's NASA speak for crashed into the ocean intentionally in 2000. It had something called AXAF. It's now called the Chandra X-ray Observatory. That was launched in 1999 and is still operating. And it had what was then called SIRTF, now we call the Spitzer Space Telescope. That was launched in 2003. So 3 of the great observatories are still operating. And they have revolutionized our understanding of the universe, partly through pictures, but a lot through spectroscopy. And this was a brilliant marketing ploy. And let me tell you one little anecdote. When I left NASA headquarters in 1996, I went back to Caltech. And I was allowed at that point to go lobby on Capitol Hill. I couldn't do that as a NASA person. And I remember that one of the SIRTF Science Working Group meetings was held back in Washington, and so a bunch of us banded together. It was well planned in advance, and we went to Capitol Hill, and we met with over 40 congressional representatives and senators. So we covered 10% of the Senate and the House in key appropriations committees. And I remember I was kind of being mentored by one of the old seasoned veterans and walked into one of the congressional offices, and they said, "Oh, hi, so-and-so. You're here to talk about SIRTF, right? The last element of the Great Observatory program." And it dawned on me at that point that putting these telescopes together and selling something called the Great Observatory program that happened to have 4 elements was a lot easier than trying to sell each telescope individually. It was a brilliant marketing ploy, and I applaud NASA management for coming up with that idea. So I talked about the 1980s decade survey from the National Research Council. Here's the one that covered the 1990s. It was called the Bicay Report after John Bicay, the lead author. And it led to the 1990s being nicknamed the decade of the infrared. And in this report, what was then called SIRTF was listed as the highest priority for a major new program in space-based astronomy. That you can read some of the highlights I put below. And one of the key reasons the 1990s was the decade of the survey is it could have been earlier. Decade of the infrared, excuse me. It could have been earlier, but the technology hadn't caught up yet. And I was back at NASA headquarters in the 1990s, and we funded academia to take sensors and detectors that had been developed for Defense Department applications to look down on Earth, and we funded astronomers and academicians to come up with clever ways of taking these detectors, modifying them, and using them for upwards-looking, low-background applications. And it was that technology development that revolutionized and made possible the decade of the infrared. And here's one of my favorite contrasting images here. So I'm old enough to remember doing astronomy and doing strip chart recorders. And here's a strip chart recording, no doubt with a bolometer attached to it, to measure the Galactic Center. And on the right is a 1990s image of the Galactic Center, which you saw earlier. And so it was this technology development that opened up this part of the EM spectrum and made infrared astronomy what it is today. And so you can contrast the difference between those two images. Now I'm going to leap forward another 10 years, and here's what the Galactic Center looks like observed by Spitzer. And unfortunately, I'm tempted to hold my computer up so you can see it. This color rendition is not the best. This is a spectacular image. It's 900 light years across, and it's, it was 16 hours of SIRTF observing time, thousands of images stitched together. It's a glorious image, and to this day, it's my desktop computer screensaver. So it was technology that made it possible. So what took so long to get SIRTF launched? Well, it was a long and winding road, and SIRTF went through a number of configurations. And just earlier today, I happened to see a report out of NASA that reported on the average length of time it took to get one of these great observatories launched after it had been recommended in the Decade Survey. And for those of us who worked on SIRTF, some people, including the project scientists, had come up with the idea back in the late 1970s and early 1980s. It must have seemed like it took forever. And the bottom line is, Spitzer was the fastest of the great observatories. The other ones, Hubble, Chandra, and what we call, and Compton, took between 17 and 19 years from the time they were recommended in a Decade Survey to the point where they were finally launched. And a lot of it has to do not only with technology development, but also with having the funding available. And particularly today, we live in a very constrained financial environment, and any hopes for future telescopes depend on completing the ones that we're building now. We don't have enough money to build more than one of these flagship missions at a time. So with SIRTF, we had to go through some painful contractions, and in fact, at one point, we were actually canceled by Congress. We started out with a concept in 1990 that was huge. It weighed almost 6,000 kilograms. It carried 3,800 liters of refrigerant, or liquid cryogen, to keep the telescope cold. We envisioned a 5-year mission and a $2 billion mission. Now, back in those days, to do infrared astronomy, you would build a telescope, and then you'd build a bigger thermos bottle and put the telescope inside the thermos bottle and launch it. And so it was leading to massive growth in the size and the mass of the telescope. And to the extent that launch costs vary as roughly mass to the 4th power, it got to be quite expensive. $2 billion, it was a lot of money in 1990. So 2 things happened that forced us to go on a diet. First of all, Hubble launched in 1990, and we all remember that fiasco, where the optical system was flawed and Hubble was a laughingstock because it couldn't take clear images. And so Congress sent NASA a very clear message after the Hubble fiasco that it would not approve any missions exceeding $1 billion. And then a couple of years later, Dan Golden became the NASA administrator and stayed on for 9 years, and he was an acolyte of faster, better, and cheaper. That was his phrase. We could do a lot of good science without spending a lot of money. And so he said, I'm not even going to ask for missions that cost more than $500 million. So we went through a couple of redesigns of SIRTF, and this closely resembles the one we ended up launching. And if I go to the next page, here's a closer example of the contrast between the big SIRTF and the little SIRTF. So it was our facility scientist who came up with a clever idea that rather than encapsulate the entire telescope in a big thermos bottle in a liquid refrigerant cooled to close to absolute zero temperatures, just launch the telescope warm, cool the instruments at the back of the telescope, and then as this cryogen vents, the vapor goes up the sides of the telescope and keeps it cold. It was a very clever design. And note in these two packages that the size of the telescope is the same. And we ended up launching Spitzer as an 85 centimeter diameter telescope in a much smaller package. So the launch mass went way down, the lifetime remained the same, the development cost was cut by 2/3, and we launched on a much smaller rocket. So in the mid-1990s, the National Research Council, after these painful diets, had to re-examine our concept, and I won't go through the text here, but they basically re-endorsed the idea as this being the top priority mission for the 1990s. So while all of this was going on, there were other infrared missions that were starting to fly. So COBE, the Cosmic Background Explorer, flew in 1989, won the Nobel Prize a few years later for validating the Big Bang explanation for the beginning of the universe. It had a couple of radio wavelength science instruments, but it did have an infrared instrument on it. IRTS was a small Japanese telescope that flew on a platform that was deployed from the Shuttle. And ISO was a program where I was the program scientist back at headquarters, the Infrared Space Observatory. It was a European Space Agency mission that took a reasonable sized telescope, put it in a much larger thermos bottle, and launched it. So things weren't standing still while we were trying to get SIRTF approved. So if you have to build a smaller version of a telescope, you have to give some things up. And so we decided in the early 1990s we were not going to try to do everything, and that we would try to focus on what we call the big four science themes. So one of them is we were going to try to gain more information on these planetary debris disks that IRAS had discovered, but we could only infer their existence. We were going to study brown dwarfs, which are failed stars. They're objects that are, roughly, they're larger than, say, roughly 13 Jupiter masses, or less than that, more than that, and they're not large enough to ignite nuclear fusion, but they're larger than a planet. We were going to study ultraluminous galaxies and active galactic nuclei, an area where IRAS had made some substantial contributions, and we were going to study the early universe. Now, interestingly, if you look at the history of the Hubble Space Telescope, or even Spitzer, as I'm going to show you at the end of my talk, when you think you know what you're going to do with a new telescope, history proves you are wrong. And in fact, the greatest legacy of Hubble, and I'm going to argue Spitzer, were in areas we did not envision. And that's partly because the gestation period of these telescopes are so long, but it's also because if you build a neat new tool and put smart people behind it, it will lead you to areas you had not anticipated. So another clever idea with Spitzer was we were not going to launch it into an Earth orbit. We were just going to ping it with enough escape velocity so it didn't come back to Earth, and we were going to let it drift behind the Earth as the Earth went around the sun. Now, why do we do that? Well, there are two reasons. Number one is we get away from the Earth and the Moon. There are three reasons, really. We get away from the Earth and the Moon, so it opens up more of the sky that we can observe at any given time. We get away from the Earth, which is a huge heat sink. We want to be cold. We have to be as cold as possible to detect the very faint heat coming from the distant cosmos. And thirdly, by getting into this kind of orbit, it allowed something we call the warm launch architecture. And so Spitzer is in this orbit. It's just drifting behind the Earth. We call it a heliocentric orbit. It's going around the sun, but so is the Earth. And it's just lagging behind the sun like a puppy lags behind somebody who's letting out a leash. And in our case, we let the leash out about 1/10 of an astronomical unit per year. So that enabled something that I showed you earlier, the warm launch architecture. And so here's a cutaway view of the telescope. Here's the primary mirror, 85 centimeters in diameter. Here's the secondary mirror. We pop the dust cover 4 days after launch. Here's the cryogen. The science instruments are in here. And you can see a solar panel, which actually not only provides power, but provides shielding from the hot sun. And these solar panels produced about 400 watts of power. That's about 1/4 of a hairdryer. But that was enough to run the instruments on Spitzer. And so here's a real live view of the telescope. That's a normal-sized person. And so you can see it wasn't huge. And you can see it was painted silver on one side and black on the other. And we always keep the shiny silver side towards the sun, so it reflects the heat from the sun. And the black side we keep away from the sun. It radiates away from any heat that has impinged on the telescope. So you can read some of the details here. By this point, our lifetime goal was 2.5 years, or our lifetime requirement was 2.5 years. We were hoping it would last for 5, and I'll come back to that. So here are the 3 science instruments we flew. They were competitively solicited and selected. So we had an infrared spectrograph built by Jim Houck at Cornell University, the multi-band imaging photometer built by George Aricki at the University of Arizona, and the infrared array camera by Giovanni Fazio at Harvard. And I'm not going to go into this instrument summary table other than to mention two things. To observe in the infrared, we can't just use CCDs. We have to use specially prepared, what we call doped sensors or detectors. And so they have all kinds of funky elements in them. And these are almost handcrafted, at least they were back then. Nothing like what we have today. The other point I wanted to make is the field of view is roughly 5 arc minutes by 5 arc minutes here, and then it varies down here. But Spitzer is capable of, it is best at imaging large regions of the sky, not doing pencil beam surveys. And so some of the images you see today, the spatial resolution will be not what you are accustomed to seeing with the Hubble Space Telescope. But some of the large mosaics that I'm going to show are nothing less than stunning. And so again, here's the EM spectrum. Starlight falls off like this. Dust emits out here. Here are the IRAC bands, 1, 2, 3, and 4 at 3.6 to 8 microns. The infrared spectrometer covered this region, and the MIPS covered these 3 bands out here. And here's the team that did Spitzer. So I've mentioned some of these partners already. JPL was the managing operations center. I should mention the original concept for SIRTF was at Ames Research Center. And it was moved for a variety of reasons down to JPL in about 1990 or so. The principal investigator moved to JPL. And so the inspiration for this mission started across the freeway over here. And the SIRTF Science Center, where I worked, was down at the Caltech campus. So we launched in August of 23. It was obviously a night launch. And the image on the left is the standard beauty shot by the NASA Public Affairs Office using a workhorse rocket, the Delta II rocket. I brought an infrared video camera with me to the Cape for this launch. And I talked my way to a preferred viewing spot. Normally you go to a launch at Kennedy and you're anywhere between 5 and 10 miles away. That's as close as you could get. But when I explained I was going to put together a little project here, they let me get within 2 miles of the launch site. And I've never been closer for any subsequent launch at the Cape. And that's what it looks like in the infrared. And you can tell we passed through a cloud layer here, and then it popped out again. So what you're seeing is thermal infrared emission there. So how did SIRTF become Spitzer? Well, like many observatories now, we ran a public contest. People wrote essays. SIRTF was a very clunky acronym. We didn't want to keep that name. We wanted to rename it something else. So we ran a contest. We had 6,000 essays come in. And I put together a rather esteemed group of people, which included author Timothy Ferris. And they narrowed it down to about half a dozen names. And we submitted those to headquarters. And it was named the Spitzer Space Telescope in honor of Lyman Spitzer, who was, some of you may know, a famed astrophysicist at Princeton University. Another Renaissance man. He studied stellar dynamics, plasma physics, fusion, and he was the first, as you can see in this image in the center here, to propose putting telescopes in space. And he proposed it in 1946. And it turned out the person who, the science director at NASA headquarters, who eventually selected the Spitzer name, worked alongside Lyman Spitzer for many years at Princeton. And I can't help but wonder to this day if, in fact, not for the inconvenient fact that Spitzer was still alive in 1990, whether the Hubble Space Telescope might have been named after Spitzer, and Spitzer might be named something else. NASA had a regulation back then that telescopes could only be named after deceased persons. And so we're fortunate to have such an honest and honorable man and his name attached to this telescope. He was an avid mountain climber, and even to this day, the American Alpine Club runs a competitive competition for people who want to do unusually challenging ascents of mountains. And a grants program is named after Lyman Spitzer. So once we moved to Spitzer, that immediately made this image a collector's item. So this is me just a couple of years ago with Jim Fanson, who was then the lead engineer on Spitzer and then later became the Kepler project manager at JPL. And he always told me one of his goals was to get the two of us together with our respective California license plates. So he brought it up with him on Southwest Airlines. And that picture was taken a couple of years ago. So now let me stop talking about the history of Spitzer and start talking a little bit about the science of Spitzer. And I'm going to start inside the solar system and kind of work my way out through the Milky Way and into the extragalactic universe. So for the most part, we didn't take pictures of planets, because while our detectors were not the best spatial resolution, they were extremely sensitive. And so everything in the solar system was too bright to look at. But we did look at some asteroids and comets. So one of the early results was to look at a couple of Jupiter family comets, which are depicted here, Johnson on the top, Shoemaker-Levy 3 on the bottom. This is not the one that crashed into Jupiter. And the point I wanted to make here is if you were to observe these comets at visible wavelengths, you would see the tail moving towards the top, which means the sun's down here someplace. This comet didn't really have a tail. And what you're seeing at infrared wavelengths is a dust trail left by that comet as it goes around the sun. And so this thin tail of, it delineates the path of the comet around the sun. You could not see this at visible wavelengths. So this was kind of neat. You could tell where the comet's been and where it's going to go in the future at infrared wavelengths. One of the first results to come out of Spitzer, in fact, our introductory news conference in Washington in late 2003, was we pointed at Fomalhaut, which is the 18th brightest star in the sky. And IRAS had observed it and inferred the presence of a disk of dust around this star. We couldn't see it because we didn't have the spatial resolution. We don't have a whole lot here, but you can actually see extended emission. And so clearly there's some kind of extended dust emission circling this star. And that dust ring is almost 400 AU in diameter. So it's 5 times larger than the solar system. And we could even see an asymmetry in the ring. That may be due to some asteroid collisions in that disk, if we think it's the materials for which solar systems are made. Or it could be due to the gravitational influence of some unseen planet. And here, at roughly about the same time, a ground-based submillimeter telescope pointed at the same object, and you could see kind of like a donut around Fomalhaut. And this image just came out from the Hubble Space Telescope last year. And I just want to digress and show one HST image. So again, what we're doing is using a coronagraph, which is a mask, to blot out the light from the bright star, and we're looking at what's left. And what we see is a ring of dust around this star. And more importantly, we see a blotch. And that blotch has moved consistently in an orbit that is modeled to be in the plane of that ring of dust. So this is believed to be the first image of a planet around another star. It's moved slightly along this orbit between 2004 and 2012. Turns out to be a planet, if it's real, that has a 2,000-year orbital period. This is the only graph I think I'm going to show in the rest of this talk. So one of the most important results early in Spitzer was to look at a wide variety of stars, close-by stars. And so one of the guaranteed time observers, in fact, one of the instrument builders did exactly that. He looked at almost 300 stars, main sequence stars. And he got the age of these stars either by looking at isochrones from the Hertzsprung, from the HR diagrams or from the literature. And he plotted the disk brightness as a measure of the size of the disk versus the age. Now, before this was done, we used to think planetary formation was a relatively fast process in astronomical time. We thought all the dust circling a star as it's born, particles run into each other, they coagulate, they get larger, eventually you get planets out of this mix. We thought it took maybe 10 million years max. And what we see here are disks in stars that are a couple 100 million years. So this revolutionized our view of how chaotic planetary formation was. It was not a simple process, and it was not a quick process. Now let me go back to, this is an artist's depiction, and so I showed you earlier that if you just measure the total radiation from a star, it's going to fall off as you go to longer wavelengths. Here's a clever way by which you can infer the presence of disks around stars even when you cannot see them because you do not have the spatial resolution. So here's what you would expect if you only had a star. Here's what IRAS saw. It saw the stellar light, but a bunch of other stuff. So we could infer that there's cooler dust at longer wavelengths emitting at infrared wavelengths. And you can even infer if there's a gap in here, perhaps caused by a planet sweeping the material. You can infer that because that will drop the inner part of this curve, but not the outer part. So just by playing games here and looking at broadband spectra in the mid-infrared, we can say something about the nature of planetary debris disks around stars. And with Spitzer, we started doing some chemistry with a spectrometer on board. And so here we are from near-infrared to mid-infrared wavelengths. Here's a simplified plot of what we measured in a couple of these debris disks. And we see materials that we expect to see. We see silicates, absorption due to silicates. We see methanol, we see water ice, we see carbon dioxide. These are the building blocks of planets and maybe even future life. And we see them consistently within dusty disks around young stars. And so Spitzer has taken the first steps towards characterizing the chemistry and potentially the life-bearing potential of planets around other stars. Here was an image of a nebula that we took and released very early on. I like this picture so much it was my screensaver for a couple of years. It's the Elephant's Trunk Nebula. It's a composite of the 4 bands in the IRAS camera. So we artificially colored, we can't see any of this with our eyes. So we have to artificially color them. And so in band 1 we used blue, in band 2 we used green, band 3 was orange, band 4 was red. This is traditional. And this is the composite image we get. And we see it looks like a running man here. It's relatively red. So we're looking at relatively cool emission from dust grains. And in fact, what we think is happening is there's a very bright star off to the left side here, and the solar wind, or the stellar wind, from that star is blowing the dust and giving it this really cool pattern. And you can see the contrast between the infrared view and the optical view. So at optical wavelengths, I can't see it too well from here, but you can see it's mostly dark. with a few foreground stars. You can see through that darkness and see young stars in the midst of this dust. Here's what it looks like at different wavelengths. So that's the image I just showed you. If you go to longer wavelengths, we observed it with Spitzer, it looks like this. If you combine the two, look at what pops out. And again, I hope it looks like pink to you. There should be all kinds of pink spots here. These are newborn stars, and I've circled a few of them here. Protostars, probably no more than a few million years old. And so we can see protostars being formed with Spitzer. And this is turning out to be something, a wonderful finding chart for something like ALMA, which is a new ground-based submillimeter array, which just opened for business last year in Chile. And that telescope can go in and produce very high-resolution imagery and spectroscopy of these protostars. Now, before I go any further, I wanted to talk about one of the other innovations of SIRTE, Spitzer, and that is something we call the Legacy Science Program. So earlier, I mentioned when we went on our second diet, our requirement was for a 2.5-year mission. And then the refrigerant or cryogen would run out, and then we wouldn't have much of an observatory anymore, or so we thought. Well, back in those days, the mid-90s, that's before the internet and the web has revolutionized our lives, you would write a proposal to observe something on a telescope. You might get approved, you might observe it a year later. It would take you a year to write the science results, another 6 months to get it published. I mean, the whole cycle of observing on a telescope might take 2.5 years. And history has shown that the most important time is not when you initially observe something, it's when you do the follow-up observations. You can start to do less discovery, more characterization. And so the idea with Spitzer was to come up with something that would get a lot of data blasted out into the community as soon as possible. So we created something called the Legacy Science Program, which I spent a lot of my time advocating for and helping define. These were large and coherent science projects of general, lasting importance to the astronomical community. So if I'm a proposer and I propose to collect data for science A, the data should be able to be used to do science B, C, and D also. And then we did something nobody had done at that time, which was instead of honoring the usual proprietary period of 1 year, we would blast the data out after we calibrated it. So we picked 6 legacy science teams and funded them for about $1 million a year for 5 years, and they helped us develop some of the pipeline data processing products we needed for the Spitzer mission. And one of those legacy science projects was something run by Neil Evans at the University of Texas called Cores to Disks. And his goal was to look at a bunch of, this is a visible light, look at a bunch of black regions in the Milky Way where we can't see anything. And lo and behold, at infrared wavelengths, we could poke right through that dust and see new protostars. Now this one looks a little funky because the spatial resolution isn't all that well, and it includes data from the MIPS instrument, which is very long wavelength. And so it's a bit of an artifact. But this wonderfully illustrated the power of Spitzer to be able to see stars forming in very complex and dusty environments. Here's one of those large mosaics I talked about earlier. And the first time I saw this, my jaw just about hit the table. So this is a much-studied star-forming region in the Carina Nebula. And there's a very bright star at the top here. And you can see all the complex structures here. And no doubt, there's stars being formed, typically in these pillars like this. And I'll show you another picture of a similar pillar shortly here. But you can contrast what this region of the sky looks like at visible wavelength. You see some, ionized gas, but it doesn't look all that exciting. It sure looks exciting at infrared wavelengths. And so what we're seeing here is a whole area where we see stars being born both singly and in groups and clusters. And here, in fact, is one of the most iconic images in the history of astronomy. You've all seen the Hubble images here. They were on the cover of Time magazine a long time ago. The pillars of creation, they were called. Of course, it's a bit of a fabrication because you can orient these however you want. Here are the Hubble images of what look like stalagmites. and here's the Spitzer imagery. So again, we were able to poke through all of the dust, and with Spitzer, we can actually see two newborn stars being formed at the edge of these dusty pillars. And so again, we have found about 20 new stars just in this relatively small region. And in fact, there's also a large number of very massive stars in this region, and astronomers actually believe these pillars may not even exist anymore. This is 6,500 light years away. And if any of those large stars went supernova sometime in the last 6,500 years, it probably destroyed these pillars just from the radiation pressure. Here's another fantastic image from one of many from another legacy science project called GLIMPSE. It basically surveyed the entire plane of the Milky Way galaxy, saw all kinds of interesting nebula. I teased Ed Churchwell, the principal investigator at the University of Wisconsin, that he took this image because it started with the letter G, and that was the name of his project. 17,000 light years away. Some kind of event here has created a shock wave that is blowing out the dust here. And in fact, anytime you have a shock and gas and put the two together, you're likely to get the physics you need for star formation. And in fact, in those circles, we've seen a couple of groups of new stars being born, which we could not otherwise see at visible wavelengths. Here is the familiar M42, Messier 42 Orion Nebula. On the right, you see a visible light image, and on the left, you see the Spitzer image. Again, you see a different vantage point and a different view of this entire region of the sky. So at the visible light, I think most of you amateur astronomers know what you're seeing here is basically ionized gas that's been heated by the ultraviolet radiation from some of the massive stars in the region. On the left, you're seeing the dust that forms future stars. And in fact, you can see three large cavities here, and I kind of circled them if you look really closely here. Three cavities there. So there's some kind of radiation and wind pressure coming from some massive stars that are clearing out the insides of these cavities. And it turns out just in this region, Spitzer has seen and identified 2,300 previously unknown protostars. And also, before Spitzer came along, we thought that up to 90% of stars in our Milky Way galaxy were formed in clusters. And it turns out that's not necessarily the case. At least in this region of the sky, we find about 60% of stars are in clusters, and about 15% are in small groups, and the remaining quarter or so are by themselves. So again, some new knowledge from Spitzer that we could not have obtained at other wavelengths. So I've been showing pictures about star birth. We have some pictures of star death. So these are some supernova pictures. On the left, you see X-ray imagery of Kepler's supernova on the 400th anniversary of the event. So these were taken in 2004. Chandra X-ray Observatory imagery, Hubble imagery, and Spitzer imagery. So again, the spatial resolution is not the same as Hubble, but you see a different phenomenon. And here you see a lot of dust in the shell that's moving out from the previously exploded star. And that bubble, in this case, is about 14 light years wide. So what we're seeing with Spitzer is we're just sampling a different regime, a different temperature regime of the dust. Now, it's possible to get all three great observatories, Hubble, Spitzer, Chandra, to look at the same object and combine their images. And that's what we've done here in this 2005 image. Here's Cassiopeia A, which is the brightest radio source in the sky, at least outside our solar system. This is a composite image from all three great observatories, and a spectacular image. And if you look very closely at the center, you'll see a turquoise dot that's artificially color-coded from the Chandra X-ray Observatory. That's the neutron star that exploded and created this supernova remnant. Here's one of my favorite images. It's called the Cat's Eye Nebula, for obvious reason. So, in addition to massive stars exploding as supernova, stars like our sun are going to have a more gentle death in 5 billion or so years and gradually shed their outer layers and create a planetary nebula, maybe not too dissimilar from the Cat's Eye Nebula. And so this is what this may be our fate. And these planetary nebula are spectacularly beautiful. And in this case, there's a white dwarf star in the center here, and we believe there's a lot of planetary debris and maybe even comets in this previous solar system for which havoc has been wreaked by this exploding star. Now let me go to the extragalactic universe. I'm an extragalactic astronomer for the most part. I love looking at pictures of galaxies. So this was the first image we took of Messier 81, 12 million light years away. So at the shorter wavelengths with the IRAC camera, we see the stellar distribution. We're seeing the stars. And you see this kind of gentle, smooth distribution. But as you go to band 2, or this is band 4 actually in IRAC, and even to 24 microns with the MIPS instrument, you see less of the stars and you see more of the dust and the materials that will create future stars. And so it just gives you a different sense of the contents and the senses of a galaxy, and abundantly illustrates that galaxies are more than just stars. They're dust and gas also. Here's a couple of colliding galaxies called the antenna galaxies. Visible light picture, here's the nucleus here and another nucleus down there. And these galaxies, based on numerical modeling, are thought to have been colliding now for 800 million years. And what happens, here's the infrared picture, and then here's a composite Hubble Space Telescope and Spitzer image. And here, this is a relatively new image. So it's not perfectly aligned azimuthally in the same sense as these other two. But what I wanted to point out is when you get two galaxies, stars, gas, dust, and they smack into each other on a very long time scale, you create a lot of shock waves. And those shock waves are the impetus or the catalyst for forming new stars. And this entire red region is a very active, what we call a starburst region. Stars are being formed at hundreds to thousands of times the pace we would normally see if not for these colliding galaxies. Here's a picture from a different legacy science project called the SING survey. This is M51, the Whirlpool galaxy. Again, visible light. You see a lot of the stars, and you can see some of the tracers here, dust in the spiral arms. Once you go to the IRAC camera on Spitzer, you see mostly the dust in the galaxy. And here we have a companion galaxy, very blue. That means not much dust in that galaxy and not much star formation going on in that galaxy. Here's an interesting galaxy I studied for a while called Messier 82 up in Ursa Major. And here's what it looks like at visible wavelength. It was thought to be an active, peculiar galaxy. And it wasn't until we mapped it within the last few years at near-infrared wavelengths when we came to realize, no, it's really a spiral galaxy. It's almost edge-on. And it has spiral arms. But it has these bizarre infrared light coming out. And so this is a very active galaxy, as we refer to it. A lot of star formation going on here. A lot of what we call polycyclic aromatic hydrocarbons. They're the building blocks of future life, potentially. And it's a very peculiar galaxy. And I've put in an X here, the location of the supernova that went off on January 21st of this year. You don't see it in this image, of course, because this image was taken in 2006. But this was the home galaxy of that recent supernova. One of my favorite pictures, the Sombrero galaxy. And it gets its name from the visible light image here. You see a stellar bulge. You see a ring around that stellar bulge. You see a lot of dust. And of course, once you get to infrared wavelengths, the contrast is different. It de-emphasizes the bulge, emphasizes the ring around the central bulge. And here is a combined visible and infrared light. And you can actually see, if you look very carefully here, a warp in the disk. So that suggests there's a nearby galaxy that happened to be passing through probably hundreds of millions of years ago. But it left a trace of that encounter with a warped disk around the galaxy. This is M31, the nearest spiral galaxy that resembles our Milky Way, a member of the local group. This is a mosaic of 11,000 images taken with the MIPS camera. So this is a longer wavelength image from Spitzer compared to the visible light image. It's just spectacular. You see all of the dust here. You can see the central bulge. And here's a composite of all of the MIPS wavelength channels here. If you look closely here, you'll see a hole. And I'm going to circle it there, and we think that's because one of the other dwarf galaxies in the local group probably passed through the Andromeda galaxy hundreds of millions, probably billions of years ago, and left a telltale signature of that encounter. This is a rather fuzzy picture, but I had to include it. It's just so cute. It's a couple of interacting galaxies. And again, you see, this is with the IRAC camera now. You see the nuclei of the two galaxies. You can tell they're obviously spiral galaxies. And you can see some new star formation out here like beads on a string. And again, interacting galaxies tend to be very bright at infrared wavelengths because there's a lot of star formation going on. And that's the case with this galaxy here. This is NGC 1097, so you can see a very bright bulge. There's a black hole at that center, probably 100 million suns worth of mass. You can see active star formation along the bar and the inner rings here. And you can see a companion galaxy over here. And it's possible that galaxy gravitationally encountered this galaxy because it left a bit of a hole. So it's fascinating how you can trace the encounter history of interacting galaxies, particularly at infrared wavelengths. Now I'm going to move way to the distant universe. So this is more than 3 billion light years away. And there's a little speck in the upper left-hand picture here that's 18th magnitude, far too faint to be seen with your naked eye. And this was one of the first spectra we took with Spitzer in late 2003. 14 minutes of integration. And we're looking at something almost across the universe. And what we detected was organic molecules at cosmological distances. These are the building blocks of life. And we saw it 3 billion years ago. That's about the time life formed on Earth. So this was a really neat plot because it just wowed us. It made us realize that organic molecules are common in the universe. And not just locally, but at cosmological distances. Many of you are familiar with the Hubble Deep Field and the Ultra Deep Field. Now we're looking back almost to the edge of the observable universe. 13 billion years ago. We think the universe is 13.8 billion years old. And so you see the Hubble image on the left. There's a blow up here of this spiral galaxy, and we've circled something you can't see at visible wavelengths. But as you move to infrared wavelengths, and there is a short wavelength infrared camera on Hubble, you can start to see it, but with Spitzer, even though the resolution is not that great, you see this thing really pop out. And again, this is the redshift effect. And so if you want to understand the first galaxies and stars in the universe, you need to be at very long wavelengths. And Spitzer was starting to observe some of the most distant objects in the universe. And in fact, this is as far back as we've gone. On the top is a visible light image of a region where we have clear access outside the Milky Way because there's not a whole lot of obscuration. It happens to be a hole that we observed called the growth strip. And then that's what it looks like at visible wavelengths. Down here is what it looked. We've masked all of the visible light, subtracted it, and here's what's left over. And we're starting to see very large structures in the early universe that could have become the first galaxies in the universe. And we're seeing that with reduced resolution, but nevertheless we see these structures. It's not uniform with the Spitzer Space Telescope. And here is a summary of the early universe with 3 telescopes. So most of you have heard about COBE. It won the Nobel Prize for, as I said earlier, endorsing and proving the existence of the Big Bang start to our universe. And you see the Hubble Deep Field. Now we see some of the Spitzer results that fill the gap here. And until COBE flew, one of the enduring mysteries of astrophysics is how do you get from a smooth universe in the first few moments of its creation to a very clumpy universe that we see today. We're starting to unravel that mystery. Kobe saw some of the first imprints on a very large angular scale of matter that would form future structures in the universe. And Spitzer has started to fill in the gap between these two. And in this history of the universe today and the Big Bang, the James Webb Space Telescope, when it launches in 2018, will start to poke into this regime. But I have to tell you, to get to the true dark ages, which is when the universe was about 400,000 years old to 400 million years old, even infrared light is not redshifted enough. You have to go to radio wavelengths. And we have a mission concept at Ames we will be proposing to NASA later this year called the Dark Ages Radio Explorer. And the goal is to see, for the first time, the first galaxies and stars formed in the universe. One of the other most important, now I'm going to step away from pictures just for a minute, and then I'm going to close with what I think is the most important result from Spitzer. One of the most important results, apart from the one I'm going to talk about, is providing greater accuracy to understanding how fast the universe is expanding. So it was Edwin Hubble who in 1929 discovered, in fact, that the universe was expanding. But the rate of expansion that he measured was vastly different from what we see today. And when I got into this game in the 1980s, we basically didn't even understand the expansion rate, that is the size of the universe, to within a factor of 2. And now we understand it much better, to within a factor of a few percent. And so there's a project out of the Carnegie Institution led by Wendy Friedman, who spent 500 plus hours of Spitzer observing time to look at the distant universe. And I won't go through, I could give an entire talk on just the contents of this poster. But all I wanted to leave you with is the fact that the Hubble constant, which is a measure of how fast the universe is expanding, has now been measured to exquisite precision, 74 kilometers per second per megaparsec. Hubble had done a key project on this earlier, and the uncertainty was 10%. So we've entered a new era of what we call precision cosmology. We now know when the Big Bang occurred to within a few percent. We know the size of the universe to a few percent. We know how fast it is expanding to within a few percent. This was almost undreamed of in the 1980s. Okay, let me close with what I think is the highlight from Spitzer, and it was completely unanticipated when we built the telescope and designed the telescope, and it's exoplanets. So many of you are familiar with the Kepler Space Telescope, finding thousands of planets around other stars, extrasolar planets, exoplanets. And so once you start discovering these things, what you'd like to do is start characterizing them, to probe their atmospheres, see if they might harbor biosignatures, evidence of life. And we are taking the first baby steps on that path with the Spitzer Space Telescope. So let me explain how this works. And so keep in mind, we do not have the spatial resolution or visual acuity to image these planets with Spitzer. And in fact, all we see is the combined light from a parent star and any planets it might have around it. And so down here, this is how Kepler works. It stares at stars at visible wavelengths. It waits for a planet to pass in front of the star, slightly diminishing the total light that you see. Kepler can't see these planets. All it sees is the diminution of the light as that planet passes in front of the star. Spitzer does the reverse of that. And that's because the contrast at visible wavelengths between a planet shining reflected light and the parent star is about a billion, a factor of 1 billion. At infrared wavelengths, that contrast is only 1 million, and it's due in part to the fact that the planet is actually emitting infrared light or heat. It's not just solely reflecting the light from its parent star. And so with Spitzer, what we do is we take a measurement of the star and the planet. Here's the combined spectrum. And then we wait for the planet to go behind the star. We take another one, and we subtract the two. And whatever's left has to be due to the planet, right? As long as you've controlled your systematics well enough. And so what we're doing with Spitzer is we're waiting for planets that are known to exist, either through Kepler or ground-based surveys, and we measure the dip in light when that infrared-rich emitting planet circles behind the star. So here it is, the first light from extrasolar planets. Here's an artist's depiction of what a planet would look like as it goes behind its parent star. It's a rather drab contrast at visible wavelengths, but it's a much brighter planet in infrared wavelengths, and it leads to a diminution or a drop or decrease in total light when the planet goes behind the star. And so here's a couple of stars, 150 and 512 light years away, the first light from an extrasolar planet. Here's a measurement made in 2006 of a known exoplanet called Upsilon Andromeda that was discovered. These planets are all huge, by the way. They're what we call hot Jupiters. And they're circling their parent star in orbits of 2, 3, and 4 days. So they're very close to their parent star, and they probably are many times the size of Jupiter. So not likely to be hospitable to life as we know it. Nevertheless, we're starting to make inferences about the chemistry and the composition of the atmospheres of these planets. And in this case, the planet is so close to its parent star, it's tidally locked, and that means the same face is always facing the sun, just as the same face of the moon faces us. And so Spitzer just kept its eye on this combined planet and star emission as it went around its 3-day orbit and kept taking pictures. Photometry, really. And it could measure a sinusoidal wave here. So what we're seeing is more light just before it goes behind the planet, less as it's in front. And we could actually model this and determine there's a 1400 degree Kelvin temperature difference between the two sides of this locked planet, tidally locked planet. Here's the first global weather map from another planet, something we called HD 189 733b. Hotter temperatures are brighter in this depiction. This is a global map. It's another hot Jupiter, orbits its planet, its sun every 2 days. What's interesting about this is, and this is a technique similar to the one I just showed you, is we would expect the hottest point to be at the subsolar point right here. It's shifted about 30 degrees in longitude. And so this has been modeled, and we believe that's because there are winds on this planet of 6,000 miles per hour. That's blowing that heat towards the east, ferocious winds. Here's the same planet with a spectrum. So it's an artist's depiction on the left, very hot Jupiter, very close to its sun. Here's what the spectrum looks like in the mid-infrared. These are signatures consistent with the blue line, which is water. So we have seen water in the atmosphere of another planet. Now, this planet happens to be so hot that it's unlikely that water is going to condense into the clouds like we see here on Earth. And one of my favorite spectra here, this is the first carbon-rich world that we have seen. So this is a result from 2010. Again, a previously known exoplanet using that simple technique I showed. And here's the spectrum. You see the Spitzer data points here in blue, augmented by some other data points in yellow. And we see absorption dips consistent with methane and carbon monoxide. So, and there's a lot of carbon in this planet. By the way, this planet's orbiting a star much like our sun, but it's orbiting with a period of 1 day. So it's very close to its parent star. It's so close that it's distorted. It's gravitationally distorted. The gravity from the parent star is stripping off the atmosphere, and in some sense making it easier to observe here. So this was an interesting finding. So again, I think one of the most important legacies of the Spitzer Space Telescope will be the first baby steps we have taken to start to characterize extrasolar planets with an instrument that was not designed to do that. In fact, when we started designing Spitzer, we didn't even know there were planets around other stars. Again, Put a good instrument and some smart people behind it, and you'll do stuff you never dreamed of. So here's one man's opinion of what the ultimate legacy will be from the Spitzer Space Telescope. We were the first to do astrophysics from outside of Earth orbit. We went into deep space, and that's now where most future telescopes are going. Partly to get away from the obscuration of the Earth. At infrared wavelengths, you want to get away from the heat of the Earth. So we did astrophysics from deep space, the warm launch architecture, which I think is the future for infrared astronomy. It's the approach being taken by the James Webb Space Telescope. It's going to have a warm launch architecture, and it's going to go into deep space. We relied on passive radiative cooling to cool the telescope down to a few tens of Kelvin, and then used our precious cryogen just to cool the scientific instruments. The whole way we do science has been revolutionized by Spitzer. The legacy science program has spawned imitators. Hubble even has something called the Treasury program now, with no proprietary data periods. Other telescopes, even some on the ground, have come to realize that the best way to get science out of a telescope that has a limited lifetime is just do a lot of observing and blast the data out to the general public and to the scientific community, and get as much data out early as you can and let them noodle on that. I mentioned the early characterization of extrasolar planets. Spitzer was the first to do a statistical study of the frequency and the nature of planetary debris disks, the materials left over from planet formation. We've determined the Hubble constant, and therefore the size of the universe and the expansion rate of the universe to within 3%. Spitzer was the first telescope to release things like this, spectra. Now, they were modified heavily for public consumption, so it looks prettier than it otherwise would to a scientist. But we did a lot of spectral data releases with Spitzer. And, oh, by the way, we were the first NASA project to set up a Spanish language website, something I insisted on when I was down at Caltech. So let me leave you with that legacy and some of the more pretty pictures that I didn't have time to put in, and I'm happy to answer questions having to do with Spitzer, happy to answer questions about infrared astronomy, happy to answer questions about Ames, happy to answer any questions about NASA, not so happy to answer questions about the meaning of life.
Would you please talk a little bit about how the life of the project was extended? Was it possible to reduce the rate of dissipation of the cryogen, or did you find ways to use the telescope after the cryogen was exhausted?
Very good question. So, in fact, we did learn how to judiciously schedule observations, so we weren't constantly toggling back and forth between longer wavelength observations, which require a lot of cryogen, and short wavelength, which do not. So that was one thing we did. And in fact, I didn't mention this, the cryogen, which was supposed to last for 2.5, and we hoped to make it last 5.5. And so, lasted 5.5. And so the Spitzer Space Telescope ran out of refrigerant in 2009. However, the first 2 short wavelength channels on the IRAC camera are still operational because it's a short wavelength, they don't need to be cooled. And a lot of the extrasolar planet results I've shown you has in fact come out of the extended mission, which started in 2009, still going on. And in fact, Spitzer is in competition right now with a variety of other NASA astrophysics missions to continue their operations. And so we'll learn the result in a month or two. But for the last 5 years, it's been running without refrigerant. Yes?
With the more precise measurement of the Hubble constant, is there any new information on whether the universe will continue to expand or collapse in upon itself?
Well, when I was getting into this game in the 80s, we thought the universe could either expand or it could contract. Most people believed it would expand forever. You know, some of the COBE results suggested that model is the most consistent with the data. The surprise in the last 10 years is the discovery that the universe is actually expanding faster. And it's led to, there's something called dark matter, which comprises a big part of the universe, which we don't fundamentally understand. Now there's something that's being posited called dark energy that's causing the universe to expand even faster. We haven't a clue what that is. We have all kinds of theories. And the top priority astrophysics mission for this decade, which means it might launch by the middle of next decade, is a mission called WFIRST, the Wide Field Infrared Survey Telescope. And that will go a long ways towards starting to answer the question of what is that dark energy. So that's a real cottage industry right now. And I expect in my lifetime that the discoverer, or discoverers, there are at least 2, if not 3, of dark energy will in fact win the Nobel Prize in physics. Back over here.
A wonderful presentation, thank you. You explained that back in the 80s when the first bodies were being put in space, it's kind of fire and forget. You don't have the ability to change the technology. And sometimes it took 17, 19 years before you actually got something launched. Just curious, how does it feel for you with technology on the Earth changing so rapidly to be in such a long cycle before you could actually update something?
Well, let me mention 2 things. Number one is, because of the long development period of these missions, anytime a mission launches, it is already flying outdated technology. And that's partly because of the gestation period, but partly because NASA is very risk averse and doesn't want to fly the latest and greatest and spiffiest whatever. And so these things, when they launch, I would posit that they're probably flying 6 to 8 year old technology typically, okay? The second comment, I have to say this, I had a White House budget examiner in my office at Ames about a year ago, and he closes the door. And the first thing, he sits down and looks me in the face and says, "Do young people want to work for NASA anymore?" And I said, I'm wrestling here with, should I tell him the truth or tell him what I think he wants to hear? What I have observed here in Silicon Valley, and we have a lot of young people at Ames coming through, is they need instant gratification. They live in a rapidly evolving social universe. The tools of being social have changed so rapidly. They don't want to work on something for 15 or 20 or 25 or 30 years. They want to work on something for 2 or 3 years and then move on. And young people these days also, they don't demand the same kind of job security that I think people of my generation do. And so we at Ames are working on developing a lot of small spacecraft, rapid turnaround things that people can do in 18 months to 3 years. We do a lot of space station hardware projects, and we can bring in young people and they can get the whole design, development, launch, operations in 2 years. And that appeals a lot to younger people these days. So I think there are 2 reasons why it's going to be harder and harder to do these big missions going forward. Number one is the budget's just not going to be there. And secondly, young people are looking for a different thrill.
Thank you.
Yes?
You mentioned the James Webb Space Telescope. Are there any other infrared or other telescopes you're looking forward to?
There are. So you've anticipated my 3 overflow slides here. So one of them is an airborne telescope called SOFIA, which we are the science lead at Ames, although the airplane flies out of another NASA center down in Southern California in the desert. This is a 2.5 meter diameter telescope. So it's as big as Hubble. And you can fly it in an airplane up at about 45,000 feet, 45,000 feet, so above what you would fly commercially. You get well above most of the water molecules in the atmosphere. And we started interleaving science and operations 2 or 3 years ago. We achieved what we call full operational capability earlier this year. So that's the good news. The bad news is the president's budget, which was released in March, would defund SOFIA. That's another way of saying cancel it. And so the relatively recent news is a lot remains to be determined, but we are getting some signals from Congress that they will probably rescue this project. And it has a nominal 20-year lifetime, so it could do a lot of science. Here is the James Webb Space Telescope. Looks unlike any other telescope you've ever seen. for a couple of reasons. So this is going to launch in 2018. This is the top priority of the 2000 decade survey, so you can do the math yourself. By the time it launches, it'll be 18 years. It was too big of a telescope. It's 6.5 meters in diameter. You can't put that in a rocket shroud, so we had to build it like a flower petal, and then it'll open up once it gets into deep space. And so it's in very deep space. And so you don't need a tube around it like a typical telescope. It's comprised of 18 hexagonal segments. That's the sun shield on the bottom here, and you can see various layers which are intended to protect the telescope from the sun, which will always be down here. And when this was first proposed under a different name to NASA back in the 1990s, I was back there then, we thought this would cost about $500 million. But we nodded and winked at each other, knowing that we'd have to spend another $500 million on the technology to make this mission happen. It's an $8.8 billion telescope now. And it is really, it is the top priority of the decade survey, but we have put most of our eggs into one basket. And I recently saw an animation back at NASA headquarters of all of the deployments that have to happen to make this telescope work. And I was on the edge of my seat. It's going to be nerve-wracking. And so this better work. And if it does, though, it's going to start poking into the dark ages that I referred to earlier. You can't do it any other way except at radio wavelengths and with large infrared telescopes. And so this will hopefully fly towards the end of this decade for a nominal 5-year mission, but it may go much longer, much like Hubble has. And then the third one I wanted to mention, I briefly mentioned it, WFIRST, the Wide Field Infrared Survey Telescope. So it's interesting, here we are in the 2010s, third consecutive decade where the top priority mission of the astronomy community has been, in fact, an infrared mission. So that gets back to that joking slide I put up there. This is where the action is. And so this mission is being reconfigured recently because the National Reconnaissance Office donated a pair of 2.5 meter telescopes to NASA at no cost. And so this was intended to be a 1.5 meter telescope. So we're going to take one of these free telescopes from the spy agency and use it for astronomical purposes. But it's going to be about a $2 billion telescope, we think. And even if we get authority to proceed with this, and we can't do that until the development period for James Webb ramps down in a couple of years, this will not likely launch before 2024 or 2025. This telescope will study dark energy. It will detect extrasolar planets through a technique called microlensing, which is different than Kepler, and it will do an all-sky survey at very high sensitivity. So those are the three that are coming. One is on board now, one launches at the end of this decade, one hopefully the middle of next decade. I forgot where I pointed last. I think it's over here now.
Yeah, I noticed that in some of your pictures that some of the stars show up on the Spitzer images, but others do not. Can you give an explanation as to which stars do show up and why other stars have not been detected?
And it gets back to one of the early little plots I showed of black body radiation. So stars like our sun maximally emit in the visible wavelength. They happen to be at a temperature that peaks in the visible wavelength regime. As you go to later type, what we call later type stars, like red dwarfs, what we call M-type and K-type stars, they tend to be much dimmer, harder to see at visible wavelength, but they really pop out at infrared wavelengths. And to the extent that 75% or so of the stars in the Milky Way galaxies are in fact red dwarfs, you really need the infrared wavelengths to do a true census of the stellar content of the galaxy. So it's all a matter of different stellar temperatures peak in different parts of the electromagnetic spectrum.
And maybe a related question is really sooty stars like carbon stars. Do they show up well in the infrared, actually?
They do, but they tend to be rather faint to begin with, and so you can see them if they're nearby. But once you get beyond a few thousand light years, and the Milky Way is 100,000 light years across, they're hard to see too.
Okay, thanks.
Hi, you mentioned that you had to do some pretty specialized doping of the infrared sensors to get them to operate. And I'm wondering, what did you need to do to the telescope mirror to make it more reflective in the infrared?
Well, see my earlier comments about William Herschel. I mean, it turns out infrared light observes the same laws of physics as visible light. The real key for infrared telescopes is you're measuring thermal emission, heat. And so you need a telescope that doesn't have different kinds of materials that have different thermal expansion coefficients. So in the case of Spitzer, and I didn't have a chance to talk about it, the entire telescope is made out of beryllium, a very lightweight but strong material, and very good for infrared observing, unlike, so it's not glass like you would have on a visible light telescope. And that's primarily so we can control the thermal expansion. Everything moves together, not disjointedly, because that would upset the focus real fast. Yes?
Since the Russian asteroid explosion over the rural parts of Russia, there's been a lot of concern about near-Earth and Earth-threatening bodies, asteroids. I thought I remember reading that infrared astronomy could contribute to the finding, identifying, and tracking of Earth-threatening bodies. Can you comment on that?
Not only can it contribute, it's the optimal way of doing it. So most of the asteroids that have been discovered by at visible wavelengths, by visible, by reflection of sunlight on these small bodies. And they're in the distant solar system. You have to make a lot of assumptions about their albedo or reflectivity. It could be a few percent, it could be 50%. That's not an issue at infrared wavelengths, because at infrared wavelengths, we're seeing the actual light or heat emitted by the asteroid. So they pop out at infrared wavelengths. And so ultimately, what NASA would like to do, and there's actually a commercial firm in the Bay Area called the B612 Foundation, which is trying to raise money for a privately funded $400 million or so telescope. It would be an infrared telescope. You launch it. You put it into a Venus-type orbit, and you look out at the outer solar system, so you could see all these asteroids would be easily detected at infrared wavelengths, and you could see the ones that are coming potentially towards the Earth, which are hard to see at visible wavelengths because of the bright sun. So infrared is the way you want to do it. And NASA had a small Explorer mission. It's still operating. In fact, it operated for about a year or two, called the Wide Field Infrared Explorer, and it's called WISE actually, whatever. Wide, I have to figure out what the acronym means. And it completed its mission. They turned it off, and then people at headquarters came to the realization you just had that it is best done at infrared wavelengths. So they turned it back on, and now it's being used to detect asteroids. Yes?
With respect to our knowledge of dark matter and dark energy, how has Spitzer affected the modeling of the residual matter in the universe as you're discovering dust and other infrared emitting matter?
I think that was better done by COBE, actually, by the 1989 Explorer mission called the Cosmic Background Explorer. They had to systematically account for all of the foreground emissions so they could, understand what the faint emission from the very distant universe was. And so they really nailed it. And in fact, one of the best scientific papers I've ever read had very little to do with science and all about eliminating the systematics so you could get to the weak signal you were looking for. This has not been Spitzer was not designed to do that. I mean, I can't honestly say we've refined the dust content of the local universe, the galaxy, through Spitzer. What we've done with Spitzer is probe into those dusty regions to see stars and, dare I say, planets being formed. So there are other assets that were better poised for that kind of investigation, COBE being one of them.
I'm going to have to say only two more questions.
Okay.
Because we are running out of time in the theater.
Okay.
For the stars with exoplanets that have like really short orbital periods, are their stars usually like a certain size or type? or is it just like a lot of like a variety of stars that have
No,
them?
we see these short orbital planets, well, we see them, we infer their existence around a wide variety of stellar types. And in fact, the Kepler mission has ended formally because 2 of our 4 reaction wheels failed. We have a proposal in that we think will be approved next month to re-vector the spacecraft and use it in a different way. And when we do that, we're going to be focusing on red dwarf stars instead of sun-like stars. And we're going to do that because the red dwarf stars, we're ultimately interested in finding planets in what we call the habitable zone, an area where we think liquid water could exist because we believe liquid water is an essential ingredient to life as we know it. And so the beauty is in a sun-like star, the habitable zone is out, you know, where Earth is, 91 million miles away. And, you know, it expand, you know, on each side of that by maybe a few tens of millions of miles. And so it takes 1 year to detect a planet in the habitable zone of an Earth-type star, but you really want to see 3 detections, and so it takes multiple years. That habitable zone collapses and gets closer to the parent star when that parent star is much cooler than the sun, and a red giant is much cooler than the sun. And so we're going to be observing fields of view with what we call the repurposed Kepler spacecraft. We call it the K2 mission, that will observe 80 days in this field, 80 days in this field, 80 days in this field. And we'll see planets circling very close to their star, but some of those may be in the habitable zone, because the habitable zone gets closer the cooler the parent star is. Good question. Yes?
Okay, last question. You said that the Spitzer ran out of cryogenics 5.5 years ago, but there's still a couple of bands on it that are still working. So what astrophysics can be done with those, or astronomy, and for how long?
Well, we can run probably through the end of this decade. Ultimately, at some point, we're limited by a different kind of gas on board the spacecraft called hydrazine, which is what we use to control the reaction wheels and point the spacecraft. But all of these results, most of these exoplanet results here I'm showing you, like this one and this one and this one, were all, you know, were done primarily with the 2 short wavelength channels. And so, and you can do a lot of imagery. You know, there's a wide variety of physics problems you can attack and imagery you can do. What we can't do is some of these dust studies, because the dust is best detected at longer wavelengths, and we're no longer sensitive to that because of the lack of cryogen. All right, well, thank you very much, and thank you for having me, Andy.
I very much agree with that applause. You've done a heroic job, and I apologize that we have to leave the theater because our time is up. But thank you all for staying and coming to this lecture, and we'll see you in May for our last program.